University of Leipzig, and he's going to talk about, is that a probing or
Probe.
probing? Oh,
Probing, yeah,
probing. I don't know what it is. Non-equilibrium states. Okay.
probing non-equilibrium.
Okay. Go ahead, please.
Okay, yeah, thank you. Thanks to the organizers for inviting me speak here. And I'm going to talk about something that has to do with non-equilibrium. I would like to say this is joint work with my student Albert Passeger, and which look at for. Okay, yeah. So what I talk about actually is set in the framework of quantum theory, more precisely the Klein-Gordon field on Minkowski spacetime. And the connection to operator algebras is, of course, through the concept of equilibrium, which relates to the KMS condition, which in turn relates to the Tomita-Takesaki modular objects for phenomena algebras. Here I will consider certain types of states that I use and couple them to bit detectors to learn about their thermal or non-thermal properties. And I will point out arguments for the point of view that the asymptotic behavior of such detectors is characteristic for the volume of certain kinds of states, which then may be an indication towards a possible characterization of close to equilibrium states beyond the KMS condition. I should say such attempts previously appeared in the literature, maybe more motivated from a mathematical perspective. I will not look at that. I will more look at, yeah, a sort of physically inspired. In the end, I will make some remarks on other generalizations of the KMS condition, also physically motivated. Okay, so the setting is as follows. I will be looking at the quartized Klein-Gordon field in four-dimensional Minkowski spacetime. So for me, it's always four-dimensional. Yeah, and here I think I can be extremely brief about this. It's the standard construction of the CCR algebra for the Klein-Gordon field here, starting in the, if you like, hierarchy style with generators, abstract field operators for the algebras. And I think that should be known to almost everyone here. And then a state, this CCR algebra, a linear functional, such that one has distributional endpoint functions with the positivity and linearity properties that the Weidmann functions have, however, not the variance. Be characteristic of the vacuum state. And then one can pass to the GNS Weidmann representation, which I call here pi omega with associated Hilbert space, GNS vector, the Weidmann domain for the field operators. The field operators are the represented abstract field operators. So here they are. And in that way, you get the would be absolutely standard. Then it is a good idea to look at these exponentiated field operators, the while operators as they are also called. And once one has them, one can form the local C star algebras generated by these while operators for space-time regions by saying that this AN there, oops, no, That's the wrong button. By saying that in the usual way, you have the C-star algebra here with this Gothic A n generated by the while operators with test functions having support in the spacetime. That's the local C-star algebra. The C-star structure is independent of the chosen representation, and then you have the usual properties here: isotony, space-like commutativity, and the covariance under the action of, in this case, elements of the proper orthogonal Poincare group. Right, so now then I will look at two types of, if you like, time shifts, time evolutions. So there are, on one hand, the inertial time shifts. So you fix some time-like unit vector u, and you use that to shift in this time direction. Or you can take the Lorentz boosts, and the Lorentz boosts here in the x1 direction, and they leave invariant the wedge regions, in particular the right wedge, in the direction of x1. Yeah, and I think you know all two. You know, the corresponding automorphisms I denote by alpha t. And here are the definitions of ground state, KMS state, and vacuum state, and I think you know that very well. I have given here the KMS condition in its distributional Fourier transform version. I think you know this one. Okay, I should say though, when I talk about the vacuum state, I mean the inertial vacuum state, so the usual one which is invariant under the full Poincare. So, just as a reminder, I think there should be no one who does not know this. So, the Bizonian-Riemann theorem, there's a restriction of the inertial vacuum state to the right wedge algebra is a KMS state at inverse temperature beta equal to 2 pi for the Lorentz boosts, and therefore in the GNS representation of the vacuum state, the boosts are implemented by the Tomita-Takesaki modular group for the wedge von Neumann algebra and the vacuum GNS vector. Okay. Now, I want to talk about detectors, and now I have to say what detector is. So a detector is a quantum mechanical two-level system, one of the simplest quantum mechanical systems you can think of. So the observable algebra is just the 2x2 matrices. Can think of this represented on a Hilbert space, which is C2, and then we have a Hamiltonian, like so. So it has a ground state with energy value 0, an excited state with some energy value E. Then you can write down what the KMS states are at inverse temperature beta, like this. Well, there's also a time evolution, this representation. This is the internal evolution of the detector. And so a detector comes with its internal time evolution or internal clock effect. And here, when we have an invariant state under this time evolution, for instance, a KMS state, then quite generally I say that in the corresponding GNS representation, the generator of the time evolution is given by an operator which is called Liouvillean. We had this in Daniela's talk, denoted by this boldface L. Okay, now coupling of the dynamics of detector and field. So here, again, very similarly as in Daniela's talk, now assuming that both the detector and the quantum field are in a KMS state with respect to their individual and so far uncoupled dynamics, we can try and set up a full Hamiltonian with some interaction. So here these pieces are, if you like, the free parts of the dynamics of the quantum field and detector system when they are non-interacting, and when they are interacting, they're in an interaction term, and this lambda in front regulates the interaction strength. What is characteristic of this unruled bit detector is this particular type of coupling, the so-called monopole coupling. So here you have I have a field operator with some smeared with some test function, and here you have some 2x2 matrix. The 2x2 matrix needs to have off-diagonal terms in order to be able to induce transitions between the ground state and the excited state of the detector, otherwise it's quite arbitrary. So, and this test function for some of the results needs to have certain spectral properties, and think of that always as having small support to approximate something like a point-like detector. Okay, now there are two approaches towards the asymptotic behavior of the coupled dynamics that you are interested in. So so we have two situations that we will look at. So one is we will look at Minkowski space-time. So here I draw a coordinate and one space coordinate, and usually there is a time-like unit vector divided by u, and often we will look at a KMS state or some more general state which has as its rest frame or as its time evolution, the time shifts in this u direction. So this is what I then call inertial time shifts or inertial KMS state. And then we also have this detector which starts out at some point y in the wedge region. And then the boosts act on this point and carry this detector along such a hyperbola. So let's be y1. And yeah, so the idea is to prepare a state for the system of quantum field and detector in the far past, so at minus capital T, so some initial state. And then here in between this range of minus T to T, the interaction is is active, and later than t we have well, the resulting state after the interaction. And then you are interested what happens in the limit that you take capital T to infinity. And similarly, you do this here, except now the T coordinate is the okay, yeah, and there are two approaches to let's say you're now interested in understanding what happens to the detector in this process in the limit of large T. And usually you assume that initially you have prepared the detector in the ground state. And then what you look at is the asymptotic transition rate, which is here denoted by capital T. The transition rate that the per unit time that the detector passes from the ground state, at which it was initially at time equal minus t prepared, to the excited state. And okay, here is one term which just depends on the detector and which is not interesting. And then here is this so-called response rate per unit time factor. And it has this form. So you take the T to infinity limit. You take actually prior to that the H to delta limit, so that you can think of this detector really sitting on this trajectory. And yeah, what you then get also is here this 2-point function. And here the location of this test function and the yeah, in this case the time evolution with the Lorentz boosts needs to be calculated, or if you're in this situation, you do this along such a inertial.
So what you do, you take quantum field theory and this two-dimensional system, and you take the tensor product, no?
Yeah.
And then you want to, but so you can use time in both sides of
Yes.
the tensor product. And how this arise, this wedge evolution? So you have the wedge time.
Yes.
The modular time is a difference.
Yes.
But on the two-dimensional side, you use the same. Of course, you have just one time.
Yeah.
And
So
you compare the two situations. So you
no, I'm not necessarily comparing. These are two different situations.
different. Okay, it's different. You look together.
No. That's it.
It's fine.
They are in fact very different. Okay, so now for the Lorentz boost situation, here this one, this one, there is this famous Unruh effect, this result by Unruh, which tells you that this transition rate now has a thermal character if the quantum field state is prepared in the Minkowski vacuum state, which, as we know, for the boosts is a KMS state. And then you can also normalize the temperature when you, for instance, get closer to the edge of the wedge with this hyperbola. Then the temperature increases. It actually increases as one over the distance from the edge of the wedge. And this is all well known. So actually, however, this is not only the case if you prepare the quantum field in this vacuum state. You can also actually use a dense set of states instead and get the same result. Or you can say, okay, I perturb the vacuum state, but staying in the volume. So I apply some field operators on the GNS vector. I get a perturbation here. And then the state will change here. And actually it will change in this domain of dependence, but the perturbations will die out when I go up with the time, future and past. So that since we leave the coupling between quantum field and detector on along all the trajectory in the t going to infinity limit, what the detector picks up is those excitations, if you like, which are most abundant, and those are those thermal excitations from the vacuum state. So that gives you the intuition why actually this does not really depend on what state exactly you use, and you can do the same if you like when you're in a KMS state for the inertial time evolution, same situation. So the thermalization of the detector is a consequence of the coupling over infinite duration, as one can also show, and it doesn't reflect local thermal properties of the states in the volume of this vacuum state in the boost situation. Okay, this is one thing. Okay, one can also look at the asymptotic state of the detector. So doing this beyond perturbation theory, and there is a thermalization theorem. The question if a KMS state for the interacting dynamics fulfills the thermalization property, which means that if you start with any state in its volume, then the long-term limit under the interacting dynamics will turn out to be the KMS state. This is more or less a non-perturbative version of what I've just said. This depends only on the volume, not the particular state. And this holds if the GNS vacuum vector is the only eigenvector of the interacting Liouvillean, in which case, however, one cannot shrink the test function h to a delta in order to do this. And there are some results. There is an interesting result by De Bievre and Merkley, which has been inspiring for the whole, well, for many things. And they have shown that actually, when one takes the vacuum restricted to the wedge as the initial state for the field, then one has the thermalization property. And we have also shown what you expect that this is the case if you take an inertial time KMS state and have the coupled detector at rest in this particular inertial frame. Okay. So, and that means preparing the coupled system at t equals 0 in any state in the volume of the interacting KMS state for field and for a detector, then evolving it under the interacting dynamics to large in the limit of large times, the partial detector state will be found in a KMS state. Okay, yeah, okay. Now, in order to achieve that result, it is absolutely essential that this interacting KMS state is in the volume of the tensor product of the KMS states for field and detector with respect to the uncoupled dynamics. So now let us look at the situation. At this situation, we have prepared a KMS state for the quantum field with respect to this inertial time direction u. We will now consider a detector which moves with a constant velocity relative to this direction. And again, people have been looking, first of all, at this perturbative result, and they have derived the detector response rate. And what one can see is that it is not of the thermal form. It's not thermal. In fact, there are here some blue shift and red shift factors which enter here. So can imagine the detector moves with constant velocity with respect to a heat bath, and then there will be redshift and blue shift effects that the detector registers. And so this actually gets the detector response rate in the long term out of equilibrium. So this perturbative result has been long known. Interestingly, the authors have never given a derivation of the result in their paper. They have basically just written it down. So we have supplied one. Okay. Now, what you can also show is that actually the KMS states with respect to this u time direction, inertial u time direction, and inertial v time direction, they are properly disjoint. The folia have no intersection. This means also that the folia of when you tensor in the KMS state of the detector, again, the folia of these system states are completely disjoint. So you cannot start these return to equilibrium arguments in this situation. Yeah? So in a way, these KMS states with respect to these different inertial time directions are very, very disjoint. So this is, if you like, a proper non-equilibrium situation. You can also turn this slightly around. You can say the detector is at rest in its inertial frame, and you have a relatively moving KMS state, so a KMS state prepared in a relatively moving frame. And this is a non-equilibrium situation. So the spectrum that the detector registers in the long time limit is different from an equilibrium response rate. Actually, this together with in more than one space dimension, the aberration effects is quite important, because this way in astronomy one determines velocities of objects, luminous objects, their velocities perpendicular to the line of sight. It has some importance. and actually these non-equilibrium effects of such radiation has first been systematically studied in astronomy in this context. Okay, now I want to look at a related but slightly different situation, non-equilibrium steady states. So now you wonder maybe about one thing. We can, on one hand, have the detector exposed to a moving heat bath relative to the detector. Is that the same as a non-equilibrium steady state coupling? So the detector is at rest, and you say, okay, I do something slightly different. Instead of moving the heat bath, I create a state where there is a thermal flux from left to right in this case. So that is a non-equilibrium steady state. Quite generally, non-equilibrium steady states are stationary states of, let's say, quantum degrees of freedom in contact with several thermal reservoirs with respect to the same inertial time direction. So for each reservoir, and these reservoirs held at distant locations. So the simplest thing is here, you put you have a quantum field, and first let's say you have it in a box, and you put the left side of the box at some temperature or inverse temperature, eta L, and the right hand side you put at a different temperature. And then to have the appropriate idealization that you did not care about boundary effects, you take the distances here, or the locations of these reservoirs, of the left one to -infinity and the right one to +infinity. And one can construct this. Yeah? One can construct such states completely nicely. We have done this, and these states have good properties. They are Hadamard states. So, okay. So what then happens if you have this situation is that you have a constant heat flux in the x1 direction. It's this state varies, or that is imprinted state.
So you are always in the free field case.
Perfectly. Now, this heat flux moves with some velocity. The velocity is called this co-moving velocity, and we have calculated it here. So it depends in some way on the temperatures of the left-hand side and right-hand side reservoir in this way. This is for the massless Klein-Gordon field. And then one can look at the asymptotic detector response rates in that situation. Here we have prepared the non-equilibrium steady state with respect to the time axis u. Yeah. And now we look at a detector of which moves with a constant velocity with respect to the time axis u. So v, as in this picture. Now, if the detector is at rest with respect to the two reservoirs, you get a mixed temperature state. Response rate is the statistical average of the response rates for the left side reservoir temperature and the right side reservoir temperature. And this already indicates the detector does not pick up the heat flux. It just responds to the temperatures. And if the detector is moving with some relative velocity with respect to the defining inertial frame of the non-equilibrium steady state, well, then you get some complicated function depending on the reservoir temperatures and the velocities for this asymptotic detector response rate. Interestingly, if you move exactly with the velocity of the heat flux, co-moving frame, then the response rate does not show a thermal response rate, which tells you the detector cannot compensate the velocity for the heat flux, because it does not couple to the heat flux. So the response rate is not just the average of the response rates of detectors in the inertial motion with respect to heat baths at the inverse temperatures, which is what maybe initially one think, but it's not the case. Okay, so I will try and summarize. So the en-route UV detectors assume asymptotic response rates, which are characteristic of thermal either equilibrium or non-equilibrium properties of the quantum field state when coupled to such states and or are moving with respect to reservoirs defining such states. However, the asymptotic rates of detector states are not assumed just for specific states, but for dense sets of states. So basically local perturbations of such states are not detected asymptotically in the detector response rates. So in this sense, these asymptotic detector response rates are characteristic for a volume of certain states where there are these specific states probably present. Now, to single out these particular states, you would have to analyze how the detector approaches these response rates, and that would single out certain states. There are some caveats. For instance, the detector coupling is model specific, and local properties of states are not directly tested. Relation to other work. In some way, the en-route UV detectors with, if you also consider that you have parameters there with which you can play, mainly, for instance, the coupling strength lambda and the energy gap E, they can be viewed as a sort of pre-stage to quantum reference frames. In fact, you may see here something which is a bit similar to what Chris has been telling you in the story system and probe. So here the probe is the detector with the difference that it's not coupled for finite time or within a finite space-time region, but for all of the time. So that also means that the induced observable of such a detector does not have a defined localization. However, if one, so one idea is if one tries to really place these detectors within the setting of quantum reference frames, one could avoid or classify the model dependence of the en-route UV detector, maybe characterizing such detectors in an axiomatic. Then there are other, I wanted to make a remark concerning other work So there is, for instance, a concept of local thermal equilibrium states, which goes back to Buchholz-Ojima and Roos in 2002. And the idea here is that locally near every space-time point X, such states behave like KMS states with respect to certain inertial time directions when tested on certain selected thermal observables, which are only sensitive to thermal properties, but not to fluxes. In a later paper, my student Granzi and Nicola and I, we have shown that one can, in a way, get rid of these local thermal observables to some degree, because at least for the free field, the condition of Buchholz, Ojima, and Roos is equivalent to a local version of the KMS condition. However, this concept of local thermal equilibrium or local KMS refers to local properties of a state. So you look really at a very close neighborhood of a point. Yeah. So in a way, you can, if you want to picture this, think of a medium like a liquid or gas. And now in a liquid or a gas, you can have all sorts of excitations. Think of a macroscopic, of a drop of water or whatnot. But if you zoom in to the molecular level, you see the thermal excitations. Yeah, so this is basically this idea of the LTE states. On the other hand, when you use the detector and you have local perturbations to the equilibrium state, if they are sufficiently local, yeah, they are in the volume, and you have the detector switched on all the time, it picks up what's most abundant, namely the thermal excitations. This works for free fields. There is, well, you see, this is a sort of approaching equilibrium situations in an asymptotic way. And what's happening at the scales where you maybe could have deviations from the thermal situation, this is somehow diluted out. So if you have something more similar, like something less similar, I wanted to say is but reactions, yeah, where classically you would use the relativistic Boltzmann equations and conditions of thermal and kinetic equilibrium, maybe in an interacting situation, Schwinger-Kaldish formalism for interacting quantum fields. It's not quite clear if that can be covered by either asymptotics, but we will find out some stage. Okay, thank you.
Questions?
Oh, maybe